Okay, yeah, welcome to today's seminar. It's an honor to introduce Zhao Qin. He's going to be presenting to us on his work on multi-scale modeling of kind of very unique materials. So very excited about seeing some of the work that he's been doing. So he's currently a research scientist at MIT, has been there since finishing his PhD, at least since 2013 at MIT. Before that, he was at Tsinghua University in China, where he earned both a Bachelor's of Engineering and a Master's of Engineering in Engineering Mechanics. So kind of a root of some aspects of civil engineering in terms of civil engineering materials. So then went on to do some interesting work at MIT, and his work has been, I think, won every Best Paper award in bio-inspired materials that's out there. So two of them, the ones being bio-inspired graphene nanogut. So not quite sure what that means, but I'm sure it's exciting. And then he was a finalist in the Student Awards at the Engineering Mechanics Institute Conference at Northeastern in 2011. So it's his second time to Northeastern. And his research has been highlighted at NBC News and Scientific American. So please join me in welcoming Zhao Qin.
Thank you. Thank you, Michael, for giving the introduction. So, welcome everyone. Good afternoon, and welcome to this seminar. So today I'm going to talk about multi-scale computational modeling of biological materials with advanced mechanics. So my introduction will include characterization, designs, and synthesis of those materials. So first of all, what motivates me to look into those materials? I think most of you guys have seen this character in the movie Spider-Man. So Peter Parker actually have performed a very amazing job by using the spider silk to stop the train and to hang out between those buildings. So it must be a very strong material. So if we take the strength of the spider silk and we assume the fiber he has in the hand is like 1 inch, what kind of weight he can hold? Actually, if you do the estimation, it will be 1,000,000 Newton. What does that mean? It means 15 elephants from Asian, or 10 Peter Pan bars, or 2 NBA red line train. So that's extremely amazing because those materials have similar strengths as steel. So can we apply those materials to engineering applications? Not only spider silk, but there are many other biological materials that have amazing mechanics. For example, nacre or bone. So one of the amazing characters they feature is they have a good combination for both toughness and the stiffness. So you can have this kind of inverse banana curve that gives you some material have a good combination of those two features. But for many other engineering materials like metals or ceramics, they will be lying this banana curve. So it means they either be tough or be very stiff, but it's difficult to have a good combination of those inclusive mechanical features. So is there any way we can explore the mechanism in those biological materials and then apply those knowledge to our own design and make new materials that has stiffness, strength, toughness, as well as lightweight for our broad engineering applications? So that's my motivation to study those biological materials. And then once I start to focus on each of those biological materials, for example, this one is the nuclear membrane of cells. So you can see the nuclear membrane is in form of a network, and the network is built by those individual filaments. And each individual filament is a bundle of the subunit, and each subunit is an alpha helix coil structure stabilized by hydrogen bonds. They go across different scale levels from the angstrom scale all the way to micrometer scale. And then this structure is so complicated, we call it hierarchical structure. So there's no continuum mechanics or theory that can describe all those different structures across different scale levels. As well as for those muscle adhesion, you have the thread, but at the end of the thread, you have those multiple layers of the adhesive protein. And then those protein contribute to the adhesion between the muscle and your rock surface. Also, the spider silk, they are semi-crystalline, so it means you have the crystal part like the beta sheet structure, and you have the amorphous part like the random coil structure. So is there any method can describe all those different geometries consistently to compare and calculate their mechanics? The reason, the answer is yes. So one of the useful methods is called molecular dynamics. So we all know from our basic physics class that the entire world composed of atoms. So for molecular dynamics, the basic unit is a single atom. And then between those atoms, you have some interaction function that describe how strong these atoms interact with other atoms for their neighbor. And then for polymer or protein material, we generally use this charm force field that describe those interactions by several different terms, including the covalent bond, electrostatic interaction, and van der Waals interaction. So comparing to those quantum physics or quantum chemistry, these kind of formula greatly reduce the complexity of the atom-atom interaction, because those quantum physics or quantum chemistry people will tell you, no, it's not true. So the atom have nuclear and the electrons, and then the electron can be described by the electron density, and that determines the interaction between atoms. But that one is very, very difficult to calculate and simulate, because those electrons, they have so much complexity for calculation, and you can only use DFT to simulate a few atoms. But here, by using this kind of mathematical description and the molecular dynamics, you can simulate thousands or millions of atoms. And then you can build a full atomistic model of the protein, for example, here, by having all those interactions there. And also, you can calculate, you can use this potential and take a derivation of that to calculate the force. Once you know the force, you can apply Newton's law to predict their trajectory as a function of time. So for example, here you can start with a straight protein structure, and then it follow the physics of the interaction to fold up into a fully folded protein structure. And this kind of folded structure carry the mechanics and the other physical property of those proteins. And one important question we ask at the beginning is why those protein material, as well as other polymer material, they have such a strong nonlinear behavior. Means if you take a reference about any polymer filament, you can, and then if they do the mechanical test, you can see that usually it's like this kind of S shape of the curve. Means you have a very flexible material at the beginning, but then once you deform it, like stretch it, it becomes stronger, it becomes stiffer, because the slope of the curve gets significantly increased at some point. So my research question about this is, for many of those protein materials, they have the common structure like the alpha helix. So they generally exist in the filament system in cells, or in wools, or in our hair. So hair is made of keratin and is full of alpha helix structures, as well as hoof. So for those bottom part of the horse, so they all show this kind of string stiffening behavior. But what's the physical mechanism behind this? Why those materials can be string stiffening? So this simple simulation carried out by using molecular dynamics actually provide me the chance to look into the basic physics. So I set up the simulation, and then I start to deform this alpha helix by fix one end and apply force to the other end. And then I can see that for those hydrogen bonds, they will break apart to unfold the alpha helix structure during the deformation. And also at the same time, once those alpha helix get unfolded, they also create the possibility for those building blocks to form some new hydrogen bond with its neighbor. For example, you will see there's beta sheet structure here and here. And then those beta sheet structure are much stronger than the initial alpha helix. And then they extend through the entire peptide to make it more crystallized into the beta sheet form, and then that contributes to the large stiffness that we can observe for those alpha helical materials. So actually, by performing those kind of simulation to many different kind of alpha helix, we also able to discover some new physics or laws that could not be obtained from the experiment. For example, here we see that for long alpha helix, there's this kind of transition and lead to the stiffening behavior of the material. But for the short pair of alpha helix, they will not go under transition, but they will just slide apart from each other. But also, we can validate those calculations by comparing to experiments. So in experiment, we cannot see the dynamic behavior of the process, but we can compare the structure before stretching and after stretching. So we can use X-ray to characterize the secondary structure, so we can indeed see how alpha helix transit into beta sheet in simulation in the experiment, and that validate our simulation prediction. So also, as I said, we can build the physical description and generate new law according to this size effect that we discovered from the simulation. And also here, we can get the force extension curve from this simulation. So you can see how this curve gets such a highly nonlinear shape once it gets deformed. But for the short peptide, they just slide apart. They don't have this kind of stiffening behavior. So based on this kind of full atomistic simulation, we can extract the stress strain curve for different materials. And then according to the stress strain curve we get for this protein material, we can design coarse grain models. So the idea for those coarse grain models is we generalize these protein bundles by using a series of particles as the representative of these full atomistic protein bundle. And then we assign a nonlinear spring between the neighboring particle. Also, according to the Young's modulus and the thickness, we can observe in experiments and simulation, we can determine the bending stiffness, and accordingly, we can assign the angular spring, the material, the elastic constant for the angular turn for those coarse grain model. And by using that, we can use coarse grain model to describe the entire network of this protein structure. And we can load this network structure and see how it might fracture under external loading. So one significant observation I have made comparing to silica, which is a very brittle material, this crack propagates from the crack tip once you load it. But for this kind of network material, because of this nonlinear mechanical behavior, it actually can dissipate a lot of the deformation energy through the entire material instead of just localized at the crack tip. Also, at some point, it will start to break. But then use this coarse grain model, I can also capture the dynamic fracture process of this material, network material. So it behaves more like a rubber. So if you have a balloon and then you make a crack, so it will break, but then it breaks because of the crack propagation. But here we can actually see a movie how the crack might break for this nonlinear material, and also we can see the shock wave coming from the crack tip. So that's very difficult for experiment to directly capture the process because the speed of the crack propagation is almost the similar speed like the sound propagation. But by using this simulation, we can do a lot of studies related to those dynamic crack propagation. Or we can use the stress strain curve of the silk from the full atomistic model, and then we can take the geometry of the spider web. And by the way, this web geometry was first developed by Dr. Cranford here in the Civil Department. He published a Nature paper 2012. And then following up his work, I put those realistic the constitutive law of the real spider silk into this web. And then I can simulate the dynamic behavior of the web under the impact loading from the water droplet on the web. Moreover, this kind of coarse grain model provides a lot of degree of freedom to modify it. So not only I can compare my simulation result with nature, but I can also simulate how this water or humidity may change the mechanics in the silk itself. For example, I can use the atomistic model and see once I increase the humidity or water content in the material, it will be stiffer. So the process called supercontraction. So it actually makes the silk material stiffer than the dry state. So, but by using this model, I can quantify how much effect it might affect the deformation once the silk gets supercontracted. But more, I do not only want to simulate the world. I want to learn, as I said at the beginning, I want to learn from this world and then try to synthesize my own stuff. So that's why I switch gear also toward the 3D printing area. So I think most of you have been get access to those MakerBot printers. But at the time, once I started to focus on this topic, so I can use the printer to print polymer materials, but there's no printer available that allow me to print silk. So I developed my own printer by using some simple acrylic plates and the machine shop, and then some simple mechanical components. And then this equipment allowed me to mix the silk solution with other particles like ions or fluorescent dyes inside the solution for printing. It also allowed me to reach different designs like structures or networks or patterns. So for example, actually the printing is fully mimicking the process how spider create the silk. So if you get a close-up look at the bottom of the spider, so they have those small nozzles that squeeze out those spider fibers in the diameter of tens to hundreds of nanometer, and then they form this entire bundle. But by using this printing device, we can print some patterns. For example, this kind of zigzag pattern on top of the glove, and then it can deform together with the glove. So we have a proof of concept that we put the pattern on top of the pig skin, and then it can be used to measure the deformation of the skin, and also it can give the Poisson ratio by comparing the deformation in two directions. I can also produce those recombined silk fiber directly, and then those fiber can be so strong that can hold very heavy weight. Also, I can put the silk fiber together with carbon nanotube or graphene to make the silk become conductive. So silk itself is not a conductive material, but by combining those carbon materials, I can make it conductive. And then it will be also a porous surface and very easy to absorb humidity, like the water from the humidity environment. And then once it absorbs water, the resistance of the fiber can change. So it can apply to some sensing facility to detect the humidity change inside the environment. But one research example, I want to show how we combine this 3D printing with the modeling to get some innovation discovery. So the research topic I was very interested in was spider web. So, but I asked myself a question, so why different spiders create different webs? So for example, you can go to the tropical area like Madagascar, and you see those kind of giant spider webs. They can cross the entire river, reach to 25 meters of the scale. And then you will see that those spider webs are very, you can maybe here from this picture, you can only see those radial thread, but it's very difficult to see the spiral thread. So actually the radial thread for those webs are much thicker than the spiral thread. But you can also go to your basement or garden to find those house spiders. So their web are very different. They have almost identical diameter for the spiral thread and the radial thread. So the question is why those kind of spiders create those different designs, homogeneous design compared with the heterogeneous design. So I can run simulation. I have some preliminary prediction, but then how to validate my result? So experiment on the nature web is difficult to carry out, also difficult to repeat. So I cannot say that I do the web on this spider web, I do the test on this spider web, but on the other day I cannot repeat my test. So I need to have a consistent way to validate my model. So 3D printing provides a very good, a very useful tool to validate that. So I use by printer. I can print those spiral thread and the radial thread on top of aluminum substrate, and then I can take out the middle part of the substrate and only leave the web and the ring outside. So this is the web that I printed. So you can pass. Yeah. So I can directly apply a loading test on those web structures, and they can get significantly deformed. I can also compare directly between those 3D printed web with those computational models that I developed. Not only for deformation, this web also capture the same failure as what I have for the simulation. So for example, if you load very locally the single thread of the web, once it breaks, it only breaks a single thread. Only if you apply the load to a very large area, that can cause those diffuse failure. And this kind of localized failure have already been discussed before as the defect tolerance of the web. But here, I want to do more. I want to do the optimization. So as I said, I want to compare and ask the difference between the homogeneous design and heterogeneous design. So I can systematically change the web model from a homogeneous design, like the same diameter for the spiral thread and the radial thread, to a heterogeneous design, like for those two extreme cases. So I see that the optimized strength for single point loading, for this kind of loading boundary conditions, I reach the optimal strength by having identical spiral thread and the radial thread. But for other kind of loading condition, like if I involve many of the threads and load them together, or I deform the entire web by simulating the ring loading or winged loading, I will end up with other optimized solution. So for example, here for those two cases, the optimized design shift from this middle to this end means you need to have a very thin, small spiral thread and very large radial thread to be able to optimize the strength. So the conclusion is very clear. So the optimized solution or optimized web geometry fully depends on the loading condition. for single point loading condition, like for the house spiders, most of the time they just expect to capture small flies or the body weight of the spider itself. So they need to be a homogeneous web to reach the optimized strength. But for these tropical, the spider web in the tropical area, most of the time they need to face the afternoon rain shower every single day, or the big wind or large flies. So they need to have those take this heterogeneous design strategy to be able to be strong enough to capture the flies and other environmental impacts. So that's actually, once we finish the study, we publish in Nature Communication paper. But also, once I obtain those results, I get really excited, because by using the printing and the simulation, we can actually explain some secret in nature. So that's a very powerful tool, and I want to apply more. So I want to develop some new materials, as say. So one strategy that I've been trying to follow is to design some material that's good for fracture toughness. And then I did a lot of literature survey, and find that many of those creatures that have a very good performance for toughness have those kind of multi-layer structure. Something like nacre or fish scale, as well as lobster and bone. They all have those kind of multi-layer structure that help to dissipate the energy once there's a fracture crack tip. So I develop directly those kind of brick and mortar geometry by combining some soft material and stiff material together. And then once I create a crack and load it, it doesn't crack straightforward through the material, but it diffuses the deformation energy everywhere to make it tough enough. But 3D printing is good for demonstration, how to synthesize the actual material. For that, I need to follow nature and design some chemical synthesis process to make new material. So here, for bone, can see that it's composed of collagen and hydroxyapatite, and then they just get self-assembled into those multi-layer structure, like we can see for this brick and mortar wall. But can I use silk and hydroxyapatite to do the same job and create similar material? So before running experiment, I actually performed some modeling and simulation to guide me for those designs. So here you can see that there's 3 different simulations. They all start with the same initial geometry, but I apply different interfacial energy between the silk peptide coarse grain model and the hydroxyapatite coarse grain model. So this interfacial energy actually represents the physical surface energy, but also it reflects some flow rate, because once you increase the flow rate, it will give less time for the silk to fully relax on the mineral surface, and then that can reduce the surface energy as well. So here you can see that although it starts with the same geometry, it actually ends up with different combination. So here for this modeling, I want to say that I follow the Stokes law from the fluid mechanics to design the force applied to every single particles in my simulation. But it ends up with different geometries. For those simulation with small surface energy and high flow rate, you have a clear multi-layer geometry. But for those simulation with a high surface energy and slow flow rate, they end up with more homogeneous mixture of those 2 materials. And as I said, I want to reach multi-layer architecture, like in nature, what nature does. So here, if and then we set up some experiment to follow this process and give a very high flow rate to assemble the silk protein and hydroxyapatite mineral plates. And here is showed the setup of our experiment. So I dissolved the silk cocoon inside the formic acid solution. And then I put the hydroxyapatite together with those silk nanofibers. And then to have a very high flow rate, I put those solvent in the bottle, and then I use a vacuum to filter out the water, but just leave the nanofibers and hydroxyapatite at the bottom of the bottle. So I actually end up with this multi-layer structure. So you can see it's very clear. It has a layer of silk and layers of hydroxyapatite and through the entire membrane. And it's actually represent of this brick and mortar multi-layer structure very well. Moreover, the membrane is can be very thin, and then it looks like this. So besides toughness, so it's also very tough and strong. But besides those mechanics, accidentally we discovered this membrane is good for water filtration. So here is a short movie that shows how water filtration may be used, may be carried out by using the membrane. For the first syringe we have, so I have put the silk with the hydroxyapatite, and then it ends up with a thin membrane at the middle of this disc. So it's so thin, so you cannot clearly see it. But then, to demonstrate its effect, I put a syringe with water and fluorescent dyes inside this syringe. So the fluorescent dyes has a diameter like several tenths of nanometer. And then once I push this syringe to go through the disc, it's become very hard because I need energy input to force the water molecule to go through the membrane, but block the other particles on the other side of the membrane. So it actually ends up with just the water without those fluorescent dyes. So the reason is hydroxyapatite actually provides a good porosity to the material, but the silk provides a good strength to connect those hydroxyapatite in the membrane. That allowed me to apply such a high force or pressure to force the solvent to go toward that. And then the physical pore size in the hydroxyapatite as well as the large surface area help to block those nanoparticles to the other side of the membrane. So besides that, I got amazed by a research topic once I was teaching for a design class for undergraduate students. So I introduced them about this token beak. So many of you might have seen that on TV or on the zoo, in the zoo. So those birds, they have such a huge beak structure, right? So at the beginning, once I first look at it, I thought it's very heavy, and then I was thinking, so if it's very heavy, then the bird will be very difficult to fly. Then once I teach, I learned from the book that the density is almost like 1/10 of water. So that's very light, and then that's why the bird is capable of flying. So not only this bird, but also other flying creatures like butterfly also have very good porous feature, like this kind of porous feature. So that initiate my thoughts. So what can be the lightest material in the world? So can this lightest solid material be lighter than air? So if it's lighter than air, can we create a balloon filled with this solid material and it can self-fly? But then if that's light enough, we also need to consider the mechanical property because atmosphere may crash it if it's not strong enough. So I want to do a theoretical calculation for the extreme light of this kind of porous material. So that motivated me to look into the strongest material in the world, graphene. So graphene is very light, it's very thin, and also very strong. But graphene also very small pieces of material, so it's very difficult to apply graphene directly to engineering application because their size are so small. So I designed the strategy to put a box of graphene flakes. Of course, it's a simulation right now. So to put a box of the graphenes together with some nanoparticles, and then I increase the temperature and the pressure to force those graphenes to fuse together. So the high temperature breaks those covalent bonds, and the pressure allows those covalent bonds to reform between those graphene flakes. At the beginning, there's a lot of defects. But once I repeat this cycle and do the annealing process, many cycles, those dislocations, they can merge or migrate to form 5-7 rings dislocations instead of those big holes. So they can get an integrated structure after this kind of thermal compression process. And then I can see that after 10 cycles of this high temperature, high pressure repeat, I end up with almost like converged number of covalent bonds formed in the material. So it's almost 1.5. So that means all the carbon atoms, they satisfactorily connect to the neighboring carbon atoms to form those covalent bonds. And also I can see that once I change my applied pressure, I can also tune the density of this porous material as I get at the end. So that's actually a method I use to obtain different carbon structures with different density. But then I need to characterize the mechanics, as I said at the beginning. So I can use the MD simulation to simulate the tension loading and the compression loading on the material. And I can get a full stress strain curve for this bulk material from compression to tension test. I can get the strength of the material, and also I can get a Young's like Poisson ratio of the material. And also simulation, you can clearly see how those covalent bonds contribute to the strength and also contribute to the stiffening behavior and the large extensibility of the material. So for the simulation, I can see that by using graphene, I can reach a bulk material with a density of 0.37. So that's almost lightest material for wood. Lightest wood, but the strength of the material is very high, so it's almost 10 times of the steel. So that can be amazing lightweight material we can use for engineering applications. Also, I've tested the energy absorption of the material. So by putting a nano indenter to penetrate or deform the porous material and see how much energy it can absorb during this indentation process. I can also merge this porous material inside water and see how this diffusion of water can contribute to the energy absorption. But more, I want to build up some theory for those kind of materials. And then once I compare with this structure with the existing cellular structure, which was developed by Lorna Gibson at MIT 20 years ago, so none of those theory can be applied to this geometry because it's so different from those existing models. So for those cellular materials, either it's open cell or closed cell, they always have those truss and plate elements. So, but here, for this kind of structure, because it's a graphene, it doesn't like to form Y junction. It doesn't like to form irregular connections like these kind of junctions. It's always like a surface. So that's why I need to find other geometry that can be better used to better describe the geometry. So I end up with a geometry called gyrite. So it's a mathematical solution that's the solution of a minimum surface question. So the minimum surface question is, can you find the geometry that no matter where you define a boundary, the surface between those boundaries is always the minimum surface to connect the boundary. So this is actually a family of different geometries, but gyrite is the most symmetric one. So you can tell that from these mathematical function, you can replace x with z, and then they still be the same function. So it's symmetric for x, y, and z directions. And then how to validate and compare to say this geometry can better very well describe this material. I use the help from 3D printer. I use this mathematical geometry, and then I can form this data cloud and build a surface from the data cloud, and then I can extrude the surface to certain thickness, and then I can divide a 3D geometry. So I can generate the STL file, as you have been doing, and do the 3D printing by the layer and the layer deposition process. So I end up with multiple of those structures. So it's a massive box. So like you can see here, and then those structures have different wall thickness that define different material density for those porous materials. And then I apply to the mechanical test. So these two movies show you, just two quick movies, show you the deformation process for two different designs. So the first one is a structure composed of very thin layer of material. The second one is the material composed of a very thick layer. So pay attention here. So it's still compressing, but then as suddenly it explodes because it breaks a lot of the surface and the bond between those pieces. So they have very different mechanical process for those different designs. So this one is more deformable and break gradually, but this one's less deformable, very rigid, but can break instantaneously once it reaches to some certain level. And then once I put both the simulation results for those red points together with the 3D printed results as those hollow points and then develop the scaling law to see how the Young's modulus, tension strength, and compression strength change as a function of the density, I see those two materials actually follow the similar trend. Of course, once I compare, I also normalize by the bulk material property. So graphene and this polymer material will have different bulk density and also the basic the modulus and strength for their building block. But then their scaling law align very well, means the structure actually between those two structures are very similar, and then allow me to reach this constant scaling law. By using this scaling law, I can also extrude this end to also I compare with literature report for those graphene aerogels. And you can see also the simulation and modeling result agree with those experimental reports. But more importantly, once I have this curve, I can extrude that to the very low density, such as air, and tell directly about the modulus, strength, tensile strength, and compression strength. A little disappointing. So once I have the density the same as air, I cannot reach the one single atmosphere. But that's the disappointing thing. But one surprising thing here is for high density material, the strength and the stiffness of the material can be very high. So that's very amazing. And then once we publish this paper on Science Advance, we get a lot of attentions from different media reports, including CNN and NBC. And also MIT create those movies on YouTube, and within a few weeks, actually there's beyond 1 million viewing for those short movie. But I'm more satisfying because recently we receive a lot of emails. So people over the world, they take our my STL file and create those gyrite structures by using their own printer. So it can be a thermoplastic printer, just like MakeBot, or it can be a more precise printer, used UV light for SLA stereolithography printing. So they all end up with those gyrite structures, and they are surprised because the structure is so light. One email says it's just like a few grams, but it can hold 400 pounds of the load. So that makes me very satisfying because my work actually can be followed and be repeated by other people. So that's the end of my talk. I would like to take any questions you may have.
Any questions?
In your thermoplastic, did you have any other density of plastic material can be used, almost like approximate to air? How do you optimize it?
Yes. So you mean once I use other kinds of polymer, can I reach a lighter material, but also even lighter and even stronger?
Yes.
Here we
prediction, because you already said about this only, but I wanted to say that is that possible if we can find.
Yes. So once I do that calculation, I take the building block as graphene. So that's already the strongest material we know in the world. And also its density, I think, is light enough. Carbon is not very heavy. So that's why I got disappointed, because if graphene cannot do that, other polymer probably cannot, because they cannot be stronger than graphene. And also they cannot be, maybe there's materials lighter than graphene, but the design space is not very huge.
Can we replace portion of material by this process? I mean, you can, for example, the wood or the bamboo.
Yes.
If we have those pores and we can inject some of this, will that make something different?
Interesting. Yes. So we might not end up with a material that's lighter than air, but we can definitely enhance the material by having those kind of support inside the internal space of those materials. So for bamboo, there's channels that create those low density of the material. But yes, if we can put those structures inside the bamboo, we will not increase the material weight a lot, but we can definitely increase the bending stiffness. Yes. Thank you.
There's part of this that I can understand. So this structure that you created.
Yes.
The reason that you created the structure is you were looking for a way to model how you can assemble graphene in a
Yes.
three-dimensional space.
Not exactly. So I simulate the graphene assembly in a molecular dynamics model, because it's very hard to, we don't have the facility to compress and heat up the graphene flakes. But then I simulate the process, how it might respond to the heat and pressure. I form this structure, but the structure is not very clearly defined because there's a lot of randomness for those particles I put inside my system, and their location are not very well defined at the beginning. That's why it ends up with very random structure. But then I try to find the better mathematically defined structure to explore the basic mechanics. So I can use finite element or other kind of method like 3D printing to directly carry out the geometry and then do the test. So that's why I go to this gyride structure, because this continuous surface is similar like the graphene case. So for graphene, it's a 2D surface. Once it merges and fuse together, it still like to stay in the surface for all those carbon atoms. And then if it can reach high density, it should be a continuous surface. And then also you need to maximize the usage of the carbon atom. Then you need to have a minimal surface within any boundary. So that's quite satisfying, the mathematical description of those gyride structure. And then I do the 3D printing. And then for the scaling law, I find agreement between this printed model and the simulation result of the graphene.
So is this the optimal structure, the optimal 3D structure to create something strong in 3 dimensions out of any 2-dimensional material?
I have not systematically optimized it. And also I need to mention that this gyride or minimum surface structure is a family of geometries. So to optimize that, I need to have a better description of what kind of property to optimize. So right now, this gyride is more like a homogeneous material, so it's symmetric for all different directions. But for other minimum surface geometry, they can have some more direction related. So they might have a strong x-axis, but weaker y and z-axis. So they can be used for other kind of, so define the objective function before getting optimization will be critical here. Yeah.
In the real application, we talk about using the reinforced plastic
Yes.
to become the tendon.
Yeah.
Will this a possibility become a lighter tendon for our cable stay structure?
Yes.
Have you thinking about that? That's a big application over there.
Yes, actually, several years ago, maybe 10 years ago, once people discover carbon nanotube, people start to propose that you can set an elevator between Earth and the Moon by using carbon nanotube. It was a fantasy because carbon nanotube is hard to grow to such a high length scale, but that motivates people to study the bundle of carbon nanotube from those carbon fibers. They can still be strong enough. They are not as strong as holding the elevator between Moon and Earth, but they can apply to many different fields. So here, this kind of structure, so it might not directly form a cable that is strong enough for elevator, but it can greatly reduce the weight for many engineering materials. So for example, we can use steel or other construction materials to make those gyride structure, and then it can be light but still strong enough for certain performance. And also the porosity in the material make it have the potential to combine with other material components to have other functions. So I don't know if I have answered your question for cable or not, but
Well,
yeah.
that's a more ideal case. Like
Yeah.
when you go to civil engineering or our application,
Yeah.
you may have to suffer, or you have to balance them.
Yes.
How much the strength or the stiffness I want
Yes.
compared to how much the weight I wanted to lose.
Yes.
You have to optimize.
Yes, yes. Just like the construction, once you use concrete to make the building, it provides the strength, but it also provides the self-weight. So that can limit the ultimate height of your building or constructions. But if you have some fundamental innovation for the material, then you can have the different balance between the weight and the strength of the material.
Can you summarize a little bit about what is implication to civil engineering material? Because we have lots of audience here are civil engineers.
Yeah, so
Using your ingenuity and describe it.
yeah, yeah, there's a lot of things to say, but I want to simplify it. So I think material is very important for civil and designs, because no matter what kind of structure you design, you optimize, you always need to think about what kind of material is available to be used to capture those designs. So that's why I spend a lot of time to study innovative materials, so that can possibly provide a lot of design space for civil and for structures and mechanical designs. So that can be applied to all different designs in application. And then once you finish a design, you can use AutoCAD to have a design. You need to use method to carry out the design, right? So 3D printing is the method after design to carry out those prototype and to test, to compare with the model. So those two parts, I mean, before and after design, that's what I'm focusing on. And then I think I can provide a lot of useful tools to people to successfully design and to be crazy and innovative.
Any last questions for no?
I have one question. So, the shoe company Adidas just recently came out with a shoe called 4D. I don't know why it's called 4D, but it's a 3D printed sole shoe. Retails at $300, which is not exactly cheap. But it caught my attention because the sole is completely 3D printed. I wonder if you could get some insight or your opinion on, the shoe industry, which might be more mechanical engineering field, whether the shoe industry can benefit from 3D printing because shoes they carry a lot of pressure, lots of vibration, and lots of impact. So
Yeah.
I don't know if you have any opinion or experience with that.
Yeah, thank you. That relates to those industrial designs. So apparently those shoes are not for regular people for daily use. They actually they provide a possibility for customizing. So actually this printing technique can combine with the scanning technique to just design a unique shoes for you, but not other people. So it fits your shape of the foot and make you comfortable once you work and also do sports. So, but it might not be economically beneficial process because it's not as high as the speed of this manufacturing is not as fast as doing the mold and then do the massive production. But it can provide this unique possibility. But also, actually, I have talked to the Adidas people 2 weeks ago about those. So, and then once they design those porous features or foam shape in the bottom of the shoes, so they try to optimize the viscoelastic property of that. But then, so we might consider use those kind of structures. Right, so we can put those kind of structures also in the design. So it will be very difficult by using conventional manufacturing technique to carry out, but by using 3D printing, it actually provides a unique opportunity to directly produce those complicated geometries. Yeah.
Well, please join me in thanking Zhao Jin.
Thank you.